Hello everybody and welcome to the first talk. Congratulations, you've made it here on time. Today we are going to have Katie Bell, who is a software engineer, and she'll be doing sandboxing untrusted code with WebAssembly. If we could have a round of applause for Katie.
Thank you. Yep, that's right. I'm Katie. I'm a staff engineer at MongoDB currently. We are hiring, by the way, particularly looking for C and C++ developers, so if you know any based in Sydney. Disclaimer, this talk is about security stuff, but I'm not giving you security advice. You are responsible for your own software security. Please research and consider the trade-offs for your own situation and risks. Also, this is something I do for fun. It's not at all related to my job at MongoDB. Okay, let's talk about untrusted code. Who trusts all of the code that they run on their computer? Yeah. Should you trust all of the code that you run on your computer? Should you trust all of the dependencies that you have bundled into your apps? We tend to just kind of hope that if we're using a dependency that someone's looked at it and someone would let us know if there was some kind of malicious code in there. But mostly we have a higher degree of trust. But I'm going to start off talking not so much about, oh, maybe we shouldn't trust our dependencies, but I'm going to start off with code that you really, really can't trust, which is you let your users upload code to your website and you run it for them. In that case, you really can't trust the code. Someone might be really sending you malicious code. So imagine you work at Shopify. I don't work at Shopify, but luckily the Shopify engineers have shared some of the stuff that they've worked on behind the scenes. It is a popular online store. If you've bought stuff on the internet, you've probably used Shopify at some point. And one of the things that makes Shopify a popular e-commerce platform is that it has a lot of third-party plugins. Even if the core platform itself doesn't do what you want, you can probably find a plugin or a third-party add-on that will do that for you as well. And they do this in the pretty standard way of Shopify doesn't trust these third-party plugins and lets the third-party plugin providers run their own code on their own servers and keep Shopify's platform separate to that. So Shopify provides a REST API or a GraphQL API, they do both. And the third-party app can use that to access the data for the shops that have added that app. And they can also hook into events that happen. So when something happens, someone buys something, goes through the checkout process in the Shopify app, it calls a webhook and notifies the third-party app. So all of these things are going back and forth this way. But Shopify started to see a problem with this approach. And one is sometimes there would be a really big popular store, and that store would have a sale. And the traffic for that sale might overwhelm one of these third-party apps. And so then that third-party app stops working for that particular customer, and they're not happy either. They might see high latency from some of these third-party apps. Some of them weren't running as reliably as you'd hope that they would, and they were down some of the time. And this causes problems for Shopify's customers because these third-party apps are struggling with maybe a sudden spike in traffic when there's a sudden, 24-hour sale happening. And on top of that, some of these third-party apps wanted to be able to add logic into the core flow of the checkout process. Maybe it's calculating a discount using custom logic. And Shopify did not want to have these unreliable third-party apps as part of something as critical as the actual checkout flow of an app, or as part of something that is going to be a really poor user experience if it's even 100 or 200 milliseconds latency. So Shopify decided they wanted to be able to run these third-party app integration functions themselves on their own servers, where they could scale them up as necessary, where they could make sure that they were always available, and where they could have that control over the reliability of them. And the last thing you ever want to do is this. Please don't do this. If you have just a process that has other secrets in it or other important logic, and you're just running untrusted code, and that code has access to all the memory of that process, that's a bad idea, especially if someone could potentially upload something that is malicious and take over that particular process or get further out. You have to be careful when you're running code that you really don't trust like this. And as a spoiler, the Shopify engineers decided to use WebAssembly to solve this problem. And we will go into more detail about how they did that. So shout out to Duncan Ushke and Mitch Dickinson from Shopify for sharing what they learned in this process and how they did it, because it's been really fascinating. All right, so if you weren't using WebAssembly, what other options do you have to sandbox untrusted code? Like every cloud provider is running untrusted code all of the time. How do they do this? So I'm going to go through 3 examples of this as kind of the broad categories of approaches that you can take for sandboxing. So one is a VM or a micro VM. So the example I've chosen here is Firecracker. It was built for AWS Lambda and Fargate so that they can run very, very tiny, very lightweight virtual machines. And that is kind of the epitome of like we can run stuff that's untrusted in here, and that is the kind of top level of security. But for even the most tiny and minimal virtual machines, you're still expecting a 5 megabyte overhead of memory at a minimum, and a startup time, maybe if you're lucky from a cold start, 125 milliseconds. That is extraordinarily fast for spinning up whole virtual machines. But even then, if you wanted to run lots and lots of very tiny functions that are going to be very fast, it might be overkill for what you need. Then there's also running in separate processes, containerized processes, probably all familiar with Docker, and how you can run stuff in a separate process, and it has all of the restrictions that you can possibly place on it with what it can and can't do, but you're still running a process on a shared kernel, so it is vulnerable to kernel bugs. There have been issues with Docker where it's able to have privilege escalation. It's getting better, but also like I don't know if I would necessarily trust it for running completely untrusted code. And then there's a kind of surprise entry into this is V8 isolates. And Cloudflare in particular uses V8 isolates to run many, many edge workers, so custom code that people have uploaded to run in there as edge workers in their cloud. And they run many of these in a single process with a very low startup time and low overhead. Even the overhead, like running a container is very low overhead because you're just running another process, but even running separate processes incurs an overhead as well. And being able to run thousands of these inside a single process means they can run them extraordinarily cheaply and extraordinarily quickly. But this is not a fair comparison. One of these you're running an entire virtual machine, one of these you're just running a little bit of JavaScript. The capability of what you can and can't do inside these is quite different. And they all have different trade-offs of exactly how secure is this. Is running stuff in the same process as secure as running it in a separate process? No. Is running stuff in a virtual machine more secure than running a separate process? Absolutely. But you've got to consider the trade-offs of like exactly what you're trying to run and exactly how secure you need it to be, and how fast and efficient it needs to be. But also, if you want to run more than just JavaScript, that is also a big factor in deciding how you would want to sandbox your code. All right, going back to WebAssembly. So WebAssembly was originally built for web browsers. It wasn't really built for this, I'm sandboxing other people's code on my cloud purpose. That wasn't what it was designed for. It was designed for things like this. This is the web version of Adobe Photoshop. And they were able to use WebAssembly to take some of their image filters and image manipulation logic and compile that into WebAssembly and run it in the browser. This is kind of what it was designed for, more number crunching at near native speeds in the browser in a sandboxed and isolated way. So the web browsers can do this. This is a web standard. It works in all of the major browsers. And WebAssembly itself has this application, but we're using it for something slightly different. So WebAssembly is a compile target. You can take code that is normally compiled to your architecture's bytecode and instead compile it to a WebAssembly binary file. So here's an example. Can anyone tell me what language this is? Go? No, it's not Go. I mean, maybe it's, Assembly script. Someone said assembly script. Yes, so this is good job. It's kind of like TypeScript, but it's written essentially to be TypeScript, but compilable to WebAssembly. So I'm going to use this as an example for most of my examples because a lot of people understand JavaScript. It's kind of a lingua franca for engineers if you do anything on the web. And so this makes it a little bit easier to share code examples that everyone can understand. So we can also compile assembly script to a WebAssembly binary file. And if we take an example of what that looks like, we have our add two numbers function, and if I compile this to WebAssembly, there is a binary format for WebAssembly. This is the text representation of that binary format, so we can see what's going on. We can see that it has a add function that it's exporting. That function takes 32-bit integers and returns a 32-bit integer. And these instructions, the like local.get and the add instructions, these are the WebAssembly instructions. They are intended to be very fast, very similar to the kinds of instructions you would see on a CPU, so that WebAssembly can be implemented very efficiently on multiple different CPU architectures. Okay. So this is WebAssembly. When you're using it, it's designed to be used kind of from JavaScript in the browser. So if you're running WebAssembly in the browser, this is a little bit what it looks like. You might, or this one's using Node because it's reading from a file. So you read the WebAssembly binary, you load it in, you instantiate it, and then it has these export functions, and you can call these export functions like you would any other function and get the result. So nice and simple. We can take some code, compile it to WebAssembly, and we can invoke it from JavaScript. This is the way that WebAssembly was designed for the browser. Okay, so you can think of WebAssembly as like a tiny simulated pretend computer, has its own call stack, its own instructions, and its own byte array of memory. And the WebAssembly engine is designed so that it cannot access any memory outside of this byte array of memory, right? Anything else outside of that byte array of memory is a bug in your WebAssembly engine. And it has no functions that it can call to make system calls or access anything outside of that little byte array of memory, because it just doesn't have the capability of doing that. There's no way to, say, make a syscall from inside WebAssembly. And so it's tiny little sandbox. So it cannot access any memory outside of its own array, and it really can't do anything. It can't read-write files or use the network or spawn processes or interact with anything. All it can do is provide functions that can be called, and it can call functions that you give it, right? If I give it a function, the WebAssembly code can call that function. Otherwise, it can't do anything. It can basically just compute stuff. So this is great. We have a little sandbox. This little sandbox is designed to safely run code from the internet. So it is designed for running untrusted code. And now we can use that outside the browser as well to maybe sandbox other untrusted code other than web pages. And in order to test this out, we have a little demo tool that I've built here. It's called Snippy. It is a rock, paper, scissors bot tournament where anybody can upload a bot in the language of their choice, compiled to WebAssembly, and play rock, paper, scissors against each other. And I have a little demo running here. It says there's no tournament running. Every 30 seconds it starts a new tournament, and there's a bunch of bots. And so hopefully within the next few seconds it will start a new tournament, assuming the Wi-Fi is working. Awkward silence. Yeah, there we go. Cool. So each time it's invoking a WebAssembly function to find out what the answer is for this. Most of the bots are very dumb, as you'll notice. So how do we build this using WebAssembly? Essentially, we're letting people upload their code, and we're running it. And all of this is not running in the browser. I know this is like a web demo. It's not running in the browser. It's actually running on a cloud service. And so how do we do that securely? So let's say we take our assembly script and we say, well, okay, how about we get everybody to implement the same function? Okay, anyone can implement this function. It has to be called rock, paper, scissors, and it has to return a string, and that string is either rock, paper, or scissors. Okay, and if we compile this into WebAssembly, we get something that looks like this. And it's still very simple, right? It's still a pretty simple example. But what you'll notice is our rock, paper, scissors function is actually returning an integer. It's not returning a string. There isn't really a concept of a string in WebAssembly terms. You can't really return a string by itself. What it is actually returning is a pointer to the number of bytes, the length of this string, and then you can actually see the string rock in there in UTF-16 encoding. So it has to kind of store the string in its memory in a particular encoding and then return a pointer to that. And what you'll see is if I compile anything, generally if you have a function and you compile it with WebAssembly, your compile process will not only generate an actual WebAssembly binary, it will also generate a wrapper function or a wrapper library for it as well in JavaScript. So we have our actual like rock, paper, scissors function coming from WebAssembly here, and then this friendly JavaScript is giving us a wrapper around that rock, paper, scissors function, and you see this underscore lift string in there to kind of go, oh, it takes the pointer to the string, takes out the string, makes it a nice JavaScript string, and returns it for us. And you'll find that in whatever language you're using to compile to WebAssembly, it will probably also generate a JavaScript wrapper for you to handle that getting data in and out of WebAssembly as well. So this means that using, oops, I'm going to go to the slides. So using a WebAssembly binary for people to upload their own code is actually kind of annoying because the WebAssembly binary has some interface that's been generated by the thing that compiled it, and it's often designed to be used with a custom JavaScript wrapper that might be different across different languages as well. So the generated JavaScript code makes it nice and easy to use on the web, but if I don't want to have to run the generated JavaScript code as well, I just want to run WebAssembly, I don't want to also have a JavaScript environment to run this code, then that can be hard. Also, WebAssembly doesn't have random numbers in it generally, so I would also have to define the interface for giving a random number to the code, and that would also be a pain. That would be another thing that I would have to define that would be difficult to define across the languages that can be compiled into WebAssembly. Yeah. This is where WASI comes in, and this is not really exactly what WASI was intended to be useful for. So WASI is essentially an API designed to let you run WebAssembly programs as a regular system program. It has file system access and command line access. So it means I could write my assembly script like this. Right? It can log to standard out, and it can call a random number. And when I compile it into WebAssembly, I compile it with the WASI interfaces. I compile it to the WASI interfaces. And then I can run it like a little command line app using my wasmtime WebAssembly engine here. So I can use wasmtime to run this as a little command line app. And if I look at the compiled WebAssembly code now, we can see that because I've compiled it against the WASI API, it's calling these sort of syscall-like functions, file descriptor write, proc exit, random get, and I can write my code the way that I would normally write my code and compile it with a standardized API. And so this is using the WASI Preview 1 spec. It is an evolving specification. And it provides an API for my WebAssembly programs to use command line arguments, environment variables, clock time, random numbers, file system access. It's a pretty limited list, but also if our purpose is sandboxing, like wasn't the whole point of using WebAssembly that it couldn't do those things, and now you're telling me you just let it do those things? Not quite. The WASI API is also designed for this sandboxing capability model as well. So from the WASI spec, the goal of WASI is to define a set of portable, modular, runtime independent, and WebAssembly native APIs, which can be used by WebAssembly code to interact with the outside world. These APIs preserve the essential sandbox nature of WebAssembly through a capability-based API design. So essentially, it can have command line args, but only the ones that you give it. You have to explicitly grant it access to environment variables or set the environment variables that you want it to be able to access. You have to grant it access to the file system specific directory or specific file at a time. So it does not get any of those capabilities out of the box. You have to grant it, but this gives you a standard API for doing so in a kind of language of process that every programming language can work with. And there's quite broad language support. So if you have C or C++ code, you can compile that using WASI and run it like a command line app as well. Same with Rust, Go, AssemblyScript. For the languages on the right-hand side, the interpreters themselves or the compilers themselves can be compiled into WebAssembly with WASI and run under the same API as well. Okay, so the language support across this for something that is a preview specification is actually pretty good. All right, going back to our example rock, paper, scissors tournament, this means that we can use the standard in and standard out to be our way of the bots interacting with the system. Okay? So we have some information that each bot is given, the name of its opponent, the recent moves of the opponent, and they can read that as JSON from standard in and standard out. Whatever the last line of the standard out is, that's the move that the bot generates. So in any language, you can write something that reads from standard in and standard out, and then that can be a bot in this tournament. We can run that. All right, live demo time. Okay. So these are the bots running. There is a create page, and we have the option here to upload a WebAssembly bot. So in order to show that this is really a live demo, Who would like to see, so the options are assembly script or Rust. Who wants to see a bot in assembly script? Who wants to see a bot in Rust? Yeah, okay, cool. Yeah, I kind of thought that was going to be the case. All right, so this is our Rust example bot here, and I can compile this, and then I can run it. Well, I can probably run it with WASM time. Target, release Rust snippybot.wasm. Okay, run it. It says hello world and rock. But we also get to choose what, it's going to be a dumb bot that just picks the same thing every single time. So who wants rock? Okay, one. Who wants scissors? Oh, that's more. Who wants paper? Oh, that was pretty even on the scissors and paper. All right, I think we're going to go with paper. I think that was slightly more. All right. So we're going to rebuild that and go over here, enter with a WASM file. I'm going to call this everythingOpen bot. Select WASM file. Is this the Rust example? Target, release. Someone tell me if I do something wrong. Rust snippybot WASM. Okay, enter the tournament. All right, and if we go to the tournament, ooh, someone else has added. I didn't add segbot. That's interesting. Hopefully, when it loads. Come on. This is the problem with having a 30-second delay in your rerunning of tournaments. There we go. There should be, yep, everythingOpen bot. You got through the first round on a bye. It won the first one, but then it lost the second one. But it has picked paper every single time. Yep. So the bots aren't very smart. Most of them are either picking the same thing every time or picking a random thing. And also, so we're going to go back to the slide. Oh, yes. If I go back to the create page, if you don't want to compile and upload a WASM bot, you can also submit one in Python or JavaScript. And that will work too. So the way that this works is I've got a WebAssembly and WASI build of Python, and so I just load in the string of the Python file in there. The same with JavaScript. I've got quick.js compiled to WebAssembly with WASI, and so it can support just uploading a script as well, and it's still entirely running within WebAssembly and WASI. Okay. Audience participation, yeah, so I would like to invite you to spend the rest of the talk not listening to me and instead uploading bots. I do have a packet of snakes here as a prize for at the end of the talk. We're going to go back and we'll watch one more tournament, and whichever bot wins that, then you get the pack of snakes. You'll have to remember what name you gave your bot and then claim it when it comes back. Okay. All right, so for building this, so the web server that I'm running for Snippy is built in Rust. And it uses the WASM time Rust API for running everything in WebAssembly. This means that the uploaded WebAssembly modules are quite restricted. It gives me a lot of options for doing that. It uses in-memory streams for standard in and standard out, and standard error is not actually using the real standard out. When you run stuff in WebAssembly with WASM time, you can give it a limited amount of fuel. So that is the number of WebAssembly instructions it will be allowed to execute before it gets terminated. I've limited the time, I've limited how much memory it can use. It has no file system access, except the Python and the JavaScript bots have read-only access to the directory where I put their input file into. You could probably mock that out better as well. So if we go to our Python example, on the site you can test it before you upload it. If I do something like, let's see, a equals 0 for I in range 1,000, a plus equals 1, right? So we're just putting a kind of a loop in there. That will run fine, but if I start adding some more zeros to this, at some point it says invalid, the program ran out of fuel. It has a limit of 1 million WASM instructions. You can actually do quite a lot with that. And in the same way, if you have it just wait instead of doing instructions, it will hit the timeout. It's timed out at a second. So the bots need to run within a second. If you want to slow down the whole tournament, you can make your bot delay for almost a second. But it will just slow things down. At some point, it will get killed. If the bot ever returns an invalid result or it errors, it just gets booted out of the tournament entirely. All right. Okay. So how are people using this in the real world? This is just a toy example, but it is inspired by the real world. In particular, Shopify functions, I wanted to kind of build my own version of this. They also use WASI Preview 1, and they also use standard in, standard out, and standard error as the kind of way of getting data in and out. And if you want to have a look at how Shopify is doing this, their docs are really good. The docs specify all of the restrictions that they place on the WASM functions that they let people upload as part of their third-party apps. But people can add plugins into Shopify that are run on Shopify servers in these little WASM functions that can be inserted into parts of the flow of users using Shopify that you wouldn't normally be able to put a third-party app into, which is pretty cool. Another fun case study is in Firefox, where they found that Google, Microsoft, and Mozilla have each found independently that around 70% of security bugs in their browsers were memory safety bugs. And Firefox was particularly worried about the graphite font shaping library. This was written, I think it was written in C++, and they didn't want to spend the time to audit all of it and make sure that it had no memory bugs. They also didn't want to rewrite it in Rust, but they were also a little bit worried that a memory safety bug in this graphite library might be able to cause a security vulnerability for an entire rendering engine. So what they did was they took that C++ code, they compiled it into WebAssembly, and then using crane lift, compiled that into native code. So this is basically the JIT compiler for the WebAssembly engine, can also be used to just generate native code that you can then run. And so now it's native code that is running effectively under the same conditions that it would be running in a WebAssembly engine in order to enforce the memory safety of the WASM engine over that C++ code. And that meant they didn't have to sandbox that library in a separate process or rewrite it in Rust to have a certain level of memory safety over the top of that library. I thought that was pretty cool. There are other people using WebAssembly in production as well, letting people using it to run untrusted code. So I think Cloudflare and Fastly both have edge services where you can run small web servers in WebAssembly. Okay, so how secure are we talking? Is anything perfectly secure? Of course not. Also, not all WebAssembly and WASI implementations have the same intention of security and sandboxing. The WebAssembly engine itself is almost always very secure. You can trust the V8 WebAssembly engine. That's the one that's used in browsers. But the WASI implementation, Node has a WASI implementation, but it's specifically not designed for sandboxing, right? You can't guarantee it won't give access to the rest of the file system. They haven't put that kind of focus into their WASI implementation. But it's Node. The WebAssembly engine itself is the one from V8, so that's pretty battle tested. I use WasmTime. This is built by the Bytecode Alliance. This is designed specifically for sandboxing for this kind of situation. It's written in Rust with a big focus on memory safety, very limited use of unsafe blocks. They audit and review all the dependencies. They do fuzz testing, and they've put a bunch of thought into specter mitigations that you can read about in their own docs as well. Is it perfectly safe? No, well, there still have been vulnerabilities. They treat these vulnerabilities very seriously, but there was one a while back, you can see the critical one at the bottom here, where malicious WebAssembly code could have read a large amount of memory of the process that it's in, which was pretty scary. So generally, like all things, security and depth, don't rely on just one thing for all of your security. If you do want to use WebAssembly to sandbox stuff, be aware that this is a risk, but it does add an extra layer of protection that you wouldn't get otherwise. So if you use it in conjunction with separate processes or containers, it would be more secure than using just separate processes or containers by itself. Running stuff in WebAssembly in that process gives you 2 layers of security. Try to keep it to short-lived functions. The whole point is that it's very, very lightweight, so not so much for long-running jobs. And of course, keep an eye on it. Make sure you're able to detect and quarantine anything that's happening. But as another note, the WASI standard itself is kind of in progress. WebAssembly itself is a very stable standard. It's in all of the browsers. It's a web standard. WASI is still in the process of being developed. And so what I've been showing you so far is WASI Preview 1. There is also WASI Preview 2, for which I need to explain the component model. So currently, in a regular WebAssembly, you have these single WebAssembly modules that have imports and export functions. A component can have a richer interface. It has these interface files that specify, lets you have, say, a string as an input or an output of a function. It lets you define types and then use those types in those interfaces. So a WebAssembly component can have a more well-defined API that could then be used across languages in a more consistent manner. And a WebAssembly component can also be made up of WebAssembly components on the inside. So you can take components with their APIs, plug them together, and assemble a bigger WebAssembly component. And each component each module that's running inside this has its own separate memory space. So you could build a binary where the libraries that it's using have independent memory allocations to the rest of the app. So you could have libraries that are safe from the other code running in the same binary, or the rest of the binary is safe from the library code that you're using. There's a kind of a beautiful future in here that isn't yet realized because it's still in flux a little bit. But potentially in the future, we could have binaries where you can have library dependencies that you only have to trust to do the thing that it's doing, and it cannot break out or affect or damage anything else that's going on in the same binary, which is pretty cool. WASI Preview 2 has more capabilities, again, still under that sandbox capability-based model, for sockets, for HTTP calls. It's very cool, but again, Preview 2, it was just stabilized earlier, or last year. And so the language support across different languages isn't quite as far along as the WASI Preview 1 stuff is. Anyway, what should you do right now? Going forward, what can I take home and actually start using today? Firstly, absolutely use WebAssembly for running stuff in the browser. It's pretty awesome. Someone built, you can run little virtual machines in the browser. This is Windows 2000 running in my browser. This artwork is my own artwork. I highly recommend checking it out. It's pretty cool. They also, I find it kind of cute that you can run Windows in the browser now, but you can also run several different distributions of Linux as well if you go to that link. I would absolutely recommend using WebAssembly for sandboxing trusted code that has risks, is maybe memory safety risks, or is unstable. You can absolutely do that. I think that's a really good use of WebAssembly for sandboxing as well. And maybe use WebAssembly for small or fast untrusted functions, but again, be careful with this. The companies that are doing this have other security measures on top of this as well. Cool, but definitely don't do this. Yep. Okay, let's check out on those bots. How are we doing for time? Ooh, it's actually pretty good on time. Okay, moment of truth. Whatever the next, so we'll see. Ooh, has someone broken it? That would be awesome. Let's try refreshing the page. Here we go. Oh, no, it's just slow. All right, so cool bot that wins won last time, but we're going to wait for the next one to start. So if one of the built-in bots that I wrote wins, then coolbot can win. But we want to see it happen in action. Also, it's running all of these sequentially. So like, see how fast this is happening. It's not doing any kind of parallelism. It's just running them one after the other. And most of these bots are written in Python. So if you see, it's actually spinning up a Python interpreter for like every single one of these little emojis most of the time. Okay. Bookworm won. That's one of the built-in ones that I wrote that just picks paper all the time. Okay, who ran coolbot that wins? Yes, congratulations. I have a packet of snakes for you coming afterwards. Cool, but thanks to all the people who added bots, there's quite a few in there. Let's see. Okay, we won't wait for that again. I would like to invite all of you, I'm going to leave it running for the rest of the conference. Please try and break it. I'm glad that nobody broke it during the talk, which is good. But if you do find a way to get the bot to do something that you don't think it should be allowed to do, please absolutely do it. You can also check out the code that's on my GitHub and have fun with it, pretty much. It doesn't matter if it breaks from now on. Thank you. Yeah. I finished a little early, so I do believe there is time for questions.
Do we have a moving mic?
Yeah, just ask questions. I'll repeat them for the video.
It seems to be very unstable in terms of implementation for a particular software. As an example, WordPress got jumped on WebAssembly
Mm-hmm.
and did a WordPress demo, but another. Just to repeat for recording, it seems very unstable how different projects implement WebAssembly. So WordPress got it pretty quickly, and I think it's been more than a year it's running, whereas other Drupal is still struggling to get there. Like they doing big progress. So did you see any kind of projects like CMSs or other web stuff that's actually successful, where when it's a complex project, has a database and language in front of it, that it's actually, and do you have any examples of good and bad implementations of WebAssembly?
WebAssembly. I'd be curious I'm not actually familiar with the WordPress or Drupal uses of WebAssembly. I'm not sure what they're using WebAssembly for. Is this for plugins to the system?
No, it's the whole system. So there is a database in the backend.
So then you can run your whole your whole
WordPress demo is
your whole
actually
WordPress instance on WebAssembly.
MySQL and PHP and Apache running in WebAssembly.
Yeah, I imagine that would be quite hard. There's a lot of things like if your code uses some kind of system call that isn't supported by WASI, then suddenly you just can't compile that thing into WebAssembly. A lot of work has gone into the Python interpreter to support WebAssembly, but even then there will be some parts of Python that just aren't supported for WebAssembly because there might not be a way to do that thing in WebAssembly yet, particularly with the WASI interface being so limiting. If you are compiling it to a WASI API, because you can also compile things to WebAssembly not using that API, using your own API or some other thing. Like Emscripten is designed to run things in the browser. It only uses browser APIs. So yeah, it depends a lot on what you're trying to do. I think I've listed most of the examples that I know of where they're using WebAssembly so that people can provide small amounts of code that is run on a server in a sandboxed way. Trying to run entire stacks in WebAssembly, yeah, that would be quite hard. I think the support for that isn't quite there yet, and most of that comes down to can I run this thing like in WASI or in WebAssembly? Is the API for the system calls and things like that supported? Compiling the logic, like the actual computation stuff, is usually pretty easy. But something as complex as like running a database in WebAssembly would be quite hard. For example, I actually had a go at trying to see if it was possible to compile V8, the JavaScript engine, to WebAssembly, and ultimately just like no. It has a JIT compiler in it, and so it needs to JIT compile, and you can't just turn off the JIT compiler because that's fundamentally how the JavaScript engine works. And so it needs to JIT compile to a specific architecture, and WebAssembly is not one of those. So if you want to run JavaScript at all inside WebAssembly, you can't use Node or V8. You have to use a different JavaScript engine. So there's lots of limitations on there on like what you can and can't run in WebAssembly. Yeah, and maybe they'll be slowly pulled apart over time. What I'm excited about is that there are use cases that do work well for WebAssembly that are outside the browser. And as long as there are some use cases that are useful, there'll be more investment into the ecosystem. And as the ecosystem builds out, maybe there will be the opportunity to run apps like WordPress and MySQL on WebAssembly in the future. Yeah. There is also beta support in Docker for WebAssembly containers, which I think is going to be where a lot of that happens. Yeah. Cool. Yeah.
So just wanted to, you mentioned that obviously the API and the previews can be limiting. Have you experienced the same thing with the runtimes themselves? That obviously you're using WASMtime, but have you noticed a lot of difference between WASMtime and WASMEdge and WASMA where they don't quite match to the spec?
Yeah, I have had some issues with that because so WASMtime is made by the Bytecode Alliance, who are also the people who are working on the WASI spec itself. So WASMtime is kind of the reference implementation for those WASI specs. I have had problems where I wanted to run JavaScript in the rock, paper, scissors bot, which I actually only got working last night. So I tried to find a WASI build of Quick.js, so I would have a JavaScript engine to run stuff in. But the only one I could find was I think it was the WASMEdge one, and WASMEdge have added their own extra functions to the WASI spec for sockets. And so I couldn't run it in WASMtime because WASMtime didn't agree on the WASI spec for that. Yes, so part of the reason I use WASM is because they're also the ones in control of the spec and it follows the spec. I did find a quick.js build that does match the WASI preview 1 spec as it is written, which is what I use in the rock, paper, scissors tournament. But yes, again, when a standard is not really a standard stabilized yet, then you might find that there are some incompatibilities there, absolutely, yeah. So I tend to stick to the Bytecode Alliance ecosystem because I have had some compatibility issues with like WASM Edge and WASMA, yeah. Hopefully it will get better over time. Again, it's pretty early. Like, it's not, I have to make this distinction. It's not early days for WebAssembly itself, but it is early days for WASI, the WebAssembly system interface, yeah.
Thanks for an awesome talk. Just in terms of the upcoming WASM GC spec, like, would you know, is there any runtimes that give you access to WASI and already support the GC? Because some languages like Dart and Kotlin have chosen to like wait for GC to be able to be run or compiled to WASM.
Yep, so that's part of the WebAssembly spec itself. I believe GC is making its way through. It's definitely a lot further ahead than the component model, which might never show up in browsers, I'm not sure. Because I understand that GC was pretty important for being able to run Go.
Yeah, I know like Chrome already supports it, but I just haven't been able to find many server-side things like WASM time that support
the server-side things don't support. Yeah, I could see there being a disconnect growing between server-side WASM and browser WASM. And I think the component model might be a big part of that. The component model is only a server-side thing and it's only really a WASM time thing, whereas browsers aren't doing the component model yet, kind of at all. There is a way you can take a component model WASM binary and then like generate a JavaScript and current WebAssembly version of it for compatibility. But yeah, I don't know about the GC spec particular. I'd be interested to see if that is going to show up in WASM time at some point. Yeah. But I could see there being a future where these two things diverge quite a lot. Yeah.
Any more questions? Okie doke.
Okay.